Welcome to the next channel. So hope you must be following some of my recent video episodes on NAS operating systems, and as well as I was doing some tests on Open Media Vault, and as well as I was covering few episode or video series on FreeNAS and recently rsync and stuff like that. So today I thought let me benchmark my FreeNAS system with a sort of a memcpy performance, because often the times whenever you enable compression or else even dedupe or encryption or something like that, many times you need to do in the code memcpy happens, because the memory where you compute anything in the buffer, it should get stored in a memory space, and then often it may be copied into another memory space and stuff like that. And moreover, FreeNAS, as it launches, and the entire ZFS chunks may stay as a pool inside the memory space. So it is quite obvious, of course, they suggest or IX system highly recommend you to have at least to start with an 8 GB of memory, and provided again it is favorable if it is something like a ECC error checked memory hardware. So that's what, because the file system will be loaded into the memory space, and it will exist in the memory space as long as the system is on. So it has to be reliable at the same time, as one can understand most of these operations happens in the memory space. And moreover, if you are into systems programming and stuff like that, this is like a data structure often will be managed like a tree data structure. So you may have several blocks, and under those blocks you may have again several blocks under a specific block. And if you see the directory structure or something like in a file system, you have the entire tree data structure. So this is how it gets very complicated. You get some pointers, so it will be pointing to some other pointers, and again if you have a file or something which is divided into several blocks or chunks, again these chunks will be organized in this sort of a hierarchy. So often whenever you do any sort of operation in this space, you need to do a lot of memcopies, and you need to do a lot of such memory operation. Sometimes it can be even mem sets. If you think about setting your hard drive to 0 bytes or you turn every bit into 0, then again you need to do something like that. So this is something quite common, and if you compare this with the networking stack, in a network stack again you need to do a lot of memcopy. You think about a VPN stack, you think about something like IPv4 stack or something, many times you need to do this memory operation. You need to copy a particular packet to of a specific chunk to another packet or something like that. You need to do many times this memory operation, raw buffer memory operation. This is nothing to do like a string operation or something, because this is just a very raw memory access. So which is why it is quite critical, and unlike something in a networking stack, in a network stack things happens in a real time in a different way, versus in a storage it happens in a different way. And moreover, in a storage, as I said, the file, the entire file system and the things within the file system and everything will be represented in a tree data structure, and it gets complicated as you explore and dig deeper. So which is why it has a specific criteria to get that peak performance. And moreover, the reason I was doing this memcopy tests, and I was curious about RAM performance, because it's just not about the specs you read about the RAM hardware. It is not just the speed of your DDR4 or something, or else the latencies of your RAM or something. Several things matters. It depends on how much is the CPU cache it contains, and as well as how optimized is the CPU cache. Just because your CPU have loads and tons of cache, it doesn't mean that it is going to give an optimal performance. If they have provided excessive cache but it is not optimal, it is not going to give a good performance. Again, after that, it again also depends on the CPU to memory interconnect. How is the bus performance? Is it DDR3? How is the bus performance of DDR3 versus how is the bus performance of DDR4, and stuff like that. And moreover, if you compare again Intel versus AMD, Intel you have this quick path interconnect and stuff like that with Intel server platform, and if you compare with AMD you have this Infinity Fabric, and if you have this, if you compare with Threadripper and AMD EPIC, such processors, they have that Infinity Fabric within that CPU core in that same die. So all these things contribute to your system performance, and one of the main important thing is memcpy itself, because this is where you test the bulk of the performance between CPU to memory and anything in between. So moving on to the system, as you can see here, I have done a quick memcpy benchmark in my x86 system. This is my main x86 system. If you see here, this is my code which I have wrote, and I am not going to do any code work for this video episode, because the intent is not about how do you write such a code. The intent is all about what this performance benchmarks reveals and how we can interpret the same to assess the overall system performance. Okay, so this is the code I have done, and here I am doing multiple tests with iterations of 10 MB each iteration. I am increasing the same, and some I have done for 30 MB and some I have done for 50 MB, and some iterations I have done 50 MB, the same test with multiple iterations. So this gives an idea that in case if it is something is pushed onto the CPU cache, how the CPU cache is going to affect the performance and stuff like that. So it's the same test. When you run it in a loop, sometimes the CPU cache comes into the picture, whereas if you do unique tests each time, CPU cache doesn't comes into the picture. So all these things matters for the overall system performance. So that is how, if you compare here, if I give an overview, I'm just taking a 2 buffer, you can see here, and I'm doing a memset so that the GCC doesn't kick any sort of optimization, because if you do anything which is the same bytes or something you put, what happens is you get each time GCC optimization, and as well as any sort of polluted results you may get. So to avoid, to an extent I'm doing a way that GCC doesn't do any optimization and we get the raw performance. Okay, so after that it is doing this memcpy, and this will be measured, whereas we are not bothered about the other any stuff you do before this metric. So essentially I am computing the same and displaying. So if you jump to this performance metrics, what I got in this system. So this is an Core i7 5820K processor. This is 6 cores and 12 threads with hyperthreading. So you can see here totally 12 cores or logical threads, CPU cores. So with this I'm getting some performance benchmarks. So you can see here for 10 MB it is taking 8 milliseconds or so and so microseconds. It is not x milliseconds and x microseconds, it is either milliseconds or microseconds, because I just need, if I need higher resolution I can see in microseconds. If I just need the single rounded value, then I can see the milliseconds value. And moreover, so whenever you do performance tests on a system like this, a high performance systems, you need to take certain parameters into consideration. You may get several wrong values because the system is so fast. Each iteration it may give a varied results, and if you run this test once again you may get complete different results. So to avoid that, what you can do is you can increase the number of iterations and as well as the number of bytes you want to test, and several combinations. I don't want to go much deeper. I'm just saying, in case if you take the same code, and if I take the same code, if I run on a AMD EPIC or some Intel Xeon server or something, then I need to do some few tweaks here and there. I may need to increase it further, maybe just not 500 MB, it may be several GBs I can put, and then I can test, or else I can start with 1 GB, 2 GB, 3 GB and so on, and then I can do some tests on the same, and then I can compare with some other server. So there you get some close to accurate curve, where the curve will look more like it will be linear curve, unlike a context like this. In this case, if you see here, as I increase the number of bytes, this is for 10 MB it is 8 milliseconds, or in this microseconds it is 8099, whereas 20 MB it is showing suddenly it is reduced as 7 milliseconds. So this is what I am talking about. And if you see here again 30 MB it is showing 8 milliseconds. So this is where you may plot this on a graph and you may not get a linear graph. The reason is the CPU is so fast, and it may give any results based on the load on the CPU at that point of time. So you may not get an accurate result, whereas if you try it on a Raspberry Pi, start with just 1 MB 2 MB test, because 30 MB is so huge for something like Raspberry Pi. So keep that aspect in the mind whenever you do some sort of benchmarking and tests. You have to first see the hardware potential, and based on the hardware you can load the system, not just copy paste this code and put onto anything and expect to get some results. So if you run the same test on a server, it completely going to look different, because it is so fast. Even for 500 GB it may not load the server anywhere as well. So which is why you can see here, till here the tests are not settled down, and after that it is a linear curve. You can see here for 40 MB 9 milliseconds, 50 MB 10 milliseconds, 60 MB it is 10 plus few more milliseconds. You can see in microseconds resolution it is 10,843. Okay, so here it has increased, whereas 70 MB it is 11 milliseconds. So you can see here, and after it is after 100 MB I have bumped up to 300 MB. For the case of 300 MB it is 92 milliseconds, and 500 MB it is around 110 milliseconds. And after that I have repeated this 500 MB tests in a for loop, and in that case you can see here, you can see the source. You can see here the same test I am running it in a for loop, and here it has suddenly jumped down, it has suddenly reduced, and it is giving a curve of around 48 milliseconds. So the performance have stabilized. So this is where it may be a reason that these things are now in the CPU cache, and the CPU cache is assisting this performance boost, because at that point of time the entire stuff may stay in the CPU cache, or most of the things may happen in the CPU cache. So again, we can't conclude in a test like this, in a system like this, to properly test a system like this. Even more I can bump up. So anyway, so this itself gives a proper starting point, and this you can check with any different system, and sometimes you can check with multi-platform and stuff like that. And in this case, if you see here, it's a x86 system, but it's a Ubuntu operating system with so and so kernel. So this has the kernel version 4.15.0, and the minor version or the Ubuntu version is 36. Maybe it is 36th iteration or something. So if you see here, these things again reflects the kernel version and how the kernel is optimized versus the hardware and stuff like that. So that's what it is. So whereas if you hop on to now FreeNAS, it is based on FreeBSD, and you can't just take this source code and compile in FreeNAS, because you need to have the entire GCC installed, and of course you can use some jails and you can do the same, but I thought let me keep this server untouched, because it's a production server. I don't want to do any goof up, and I'm not a big fan of getting any sort of VMs or anything on a NAS server, because I just need it as a very reliable storage platform, and it is enough if it works as a storage server rather than doing all sorts of weird stuff, including putting any sort of media servers and screwing up actually. So I want it as lightweight as possible. I just want it as a very reliable storage server. That's it. So I don't want to run this as it is by compiling it in the FreeNAS server. So what I have done is I have installed an entire FreeBSD in my system, and this I have installed in a VM, so I can use this as a build server. So if you are into software development, you have this terminology called as target device. So if you are into embedded or real-time devices and coding and stuff like that, system software development, we call it as a target device. So in this case, the FreeNAS server is my target device, where I can run something on the target device, but to run the code on the target device, you need some build server. So in this case, this is my build server. This FreeBSD system, which I have installed in a VM, okay, it's my build server. You can see here it is my build server, whereas this is connected via this pfSense router. So okay, so this is how it has been networked. So this is my build server. You can imagine just by installing a FreeBSD, how can it can be a server or something. It is not like that. It's all about the purpose what I am using. It is not any FreeBSD desktop or something. I may use it to compile some code. Sometimes I want I'm sorry. Sometimes I want any custom C code to run on FreeNAS server. I can use this platform. I can use this server as a platform. I can do here, the entire build of the code, and then the entire compiled binary I can run it on any FreeNAS server. So that's the main intent. So I have brought that same C code here because it is platform independent C code. Okay, it doesn't have anything specific to Linux, so it is very much platform independent C code. I can compile as it is. So I was able to compile the same. I can able to get this binary. If I do ls -l, okay, you can see here it has this execute permission. So that's the binary. I have renamed that binary as _FreeBSD. So to denote that this binary is meant for FreeBSD. The target hardware for this binary is FreeBSD. So that's what I mean. So this way we got our binary for the same source code compiled in the FreeBSD platform. So this is not to be confused with the Linux variant. The Linux one, what I compiled here, is meant for Linux. You can see here ls, and I can do this memcpy, and it works in Linux. But when I copied that memcpy benchmark _FreeBSD into my onto my Linux system, but you cannot run the same because it is not meant for this operating system. See, you can get any error. Sometimes it can cause any other issues. So I suggest to better not run something which is meant for some other platform, hardware platform, not to run on something like this. And in this case, it's the same hardware platform. Even this is x86, even this is x86, but this is a FreeBSD operating system, and it's a different kernel altogether, versus this is Linux operating system, a different kernel altogether. So you need to be aware of these things. So which is why you can't run the same. But I copied to the same in this FreeNAS server. You can see here I'm currently into a different server. I have done an SSH to my Titan NAS, and inside that I can able to run the same. So when I run the same, this is what I get, the same memcpy benchmark, but this is the FreeBSD compiled binary, which is I have done it in the FreeBSD system, and I'm able to run in the FreeNAS server, and I'm able to get this output. If you analyze this curve, it is quite linear to start with. It is not like this mission, which tells already we are able to little bit saturate this server with this type of a load, unlike something like this. Okay, so to do if you get any sort of ups and downs in a curve and it is not linear, all I can suggest is start with a bit higher number. Maybe I should start with 50 MB onwards. Okay, so not like 10 MB onwards. So because the system is so fast, sometimes 10 MB and 30 MB anything can happen. Sometimes 30 MB it can do faster, sometimes 10 MB it can do slower, and it may mix up the results. Whereas if you analyze this FreeBSD variant, which I am running in this FreeNAS server hardware, okay, so FreeNAS server system, you can see here for 10 MB it is taking 5 milliseconds, and so on, so on, so on, and it is a linear curve. You can see here it is increasing after each 10 MB increments, and when I touched 300 MB it is 91 milliseconds, and 500 MB it is 135 milliseconds. In the for loop I am getting around 109 milliseconds. So there is a small reduction, but this is not a significant reduction. Something like this system, this itself tells this system have some extra cache rather than this system FreeNAS hardware or the Ryzen CPU. So due to that, what is happening is it is optimizing the performance, and if you do any operation iteratively, the same operation, then it is pumping up the performance. Although this chances of happening like this in a real world situation is quite low. It is just okay to do something in this type of synthetic benchmark, but in a real world scenario, chances of happening like this is the probability is really none, actually, I can say. So hardly once in a while it may happen, but not all the time. Okay, so anyway, this, although it has optimized, it really doesn't matter, because in a real system this scenario will never happen. Okay, so if you compare that, let's take example this 500 MB, and here it is around 135 milliseconds, whereas here it is 123 milliseconds. In 300 MB it is 108 milliseconds, and here it is taking around 91 milliseconds. So there are some cases the FreeNAS server is much faster. Again, it depends, because here I'm using a single 8 GB memory stick. Of course, it is not ECC RAM, and I'm fine with that, which I have told the reasons already. I'm not running this all the time, and I may just use it once in a while. And again, I have some other backup system in case something goofed up. It is still fine. Okay, so it is still fine. So if you see, again, there are some cases, this is working much faster. Again, there are some cases, you can see here, this system is running much faster. So in a way, you can see here, if you see here at 70 MB, the FreeNAS is around 21 milliseconds, whereas here it is just 11 milliseconds. So here it is more optimized, this Intel system with the 6 cores versus, this Ryzen processor. If you see here it is a little more taking some time, and whereas if you see, compare the benchmarks for 300 MB, it is 91 milliseconds, whereas here it is 108 milliseconds. Again, it's something to do with the operating system as well, not just the hardware platform. The operating system also should optimize this memcpy and memcomp, all this APIs in the kernel and in the C libraries. So based on that is what you get this sort of performance curve. So it is quite an interesting test, and I feel more and more, if I need any sophisticated code or plugins, if I need to self do for my FreeNAS server, you can take a bare minimum FreeBSD build environment and make it into a build server, and you can do anything like this. You can write any real tools, not just benchmarking. You can write some real tools, and you can incorporate with complete C source code, not just scripting. Of course, I have some few scripts over here, like I mentioned in my previous videos. Like I have done something for CPU temp, and this gets the CPU core temp immediately, because in the FreeNAS GUI it is not that yet well cooked yet. Okay, this is a new beta version. There are several things they are yet to do better. Okay, so this I can do, and even I can check the hard disk temperature, and of course this may not run it as a normal user, so I need to do via super user permission hard disk temp. You can see here it is pulling out the smart control or smart parameters directly from the drive, and it is displaying on the screen. So on average, since the system is not loaded, it is showing around 41 to 30 degrees here and there. So that's what. So these are fine. These are simple scripts. If I do cat hdd temp, these are simple scripts, command line bash scripts. But if I need to do something sophisticated, I can directly write a C code, a full-fledged C code, and I can do it on a build server and then push it onto this FreeNAS target hardware or the target server. So generally we work on any system software development. When you work on a board level, you may have something, a network router or something like that. It may not have entire compiler or something. So that is why we call it as a target hardware. Whereas you may have a build server which has this entire utilities, your build utilities, or the tool chain and stuff like that. So we generally call all these names. So there you can do a full-fledged software development. You can compile the same. Sometimes although you compile it in that server, you may not able to run on that server, because you may compile on x86 system, but the software what you compiled, the binary will run only on some ARM processor. You may do cross compiling on this sort of a build server, but you may run on an ARM processor and stuff like that. But whereas in this case it is not the case. This is a VM running on a Linux kernel, and if you see here, it's a FreeBSD operating system, a VM running on a Linux server, end of the day. So the code which I compiled on this VM OS, which is FreeBSD, is native to that FreeBSD. It just works fine. You can see here, even I can run this memcpy in this VM, although this doesn't make much sense, because it's end of the day VM environment. Anything can happen depending on the Linux optimization and kernel virtualization and other stuff. it matters. So it may happen anytime. Sometimes you can use this way to assess your VM performance also. So it is quite useful. But again, for me it is not much important because I'm not here to assess any VM performance. But if you want, you can do that. But the main objective is we have used a platform like this. We got through this build server, and we can run it on any target hardware platform or a device, hardware device. So that's all. So this is quite useful in case if you have some issues with the main objective of this entire text, or the conclusion of this entire stuff is it's like you want to assess the encryption performance of your NAS servers, or you want to assess some compression performance of your NAS servers. You can use some metrics like this, and you can assess the overall CPU performance assessment. It's of course we can see the CPU benchmarks somewhere, but end of the day it's just not about some CPU benchmarks. It's all about the RAM CPU interface. It's all about the RAM CPU performance. It matters. So that is why if you see my TrueNAS benchmarking mechanism, I have even benchmarked these two systems in TrueNAS, TrueBench. If you see here, this is my processor, AMD Ryzen 3 1200 versus this is my server, this is my desktop, Intel Core i7 5820K. So if you see here, I'm getting around 98 microseconds, which is around which is this green bar. You can see here it is this processor versus this is around 89.5 microseconds. So in this case I'm measuring the latency of that entire load. So lesser is better. Okay. So if you see here, this processor, in the TrueBench, I measure single thread or single core performance. I am not interested about multi-threading performance because several factors comes into the picture when you do multi-threading performance. I am not much interested in multi-threading performance because I did a way that you can test its single core performance, and then you can just multiply, and then you can get some picture with the so and so cores, how you can scale up this performance and stuff like that. So that way, if I see this is 89 versus this is 94 or 98, which again tells there is not much difference, and you should not take this much serious, because if you run this iteration, the next time it may even show as 96, the next iteration it may show around 108 or something. So that's how sensitive the system is. Sometimes suddenly if I replace this water cooled system with active air cooled heat sinks, then it may give a different performance curve. So I don't want to take these measurements much seriously. It roughly tells more or less both are same, but little bit the desktop is having that higher edge than this low performance Ryzen processor. The reason also why I took this type of a Ryzen processor is I'm not aiming for I took this Ryzen 3 1200 processor for this FreeNAS build. The reason I took is I don't want an extensive hyper-threaded processor overloading that CPU die. Instead, I need as much as possible less TDP as possible, the real runtime TDP, and as well as the overall heat dissipation and power consumption and stuff like that. So these are the main criteria. Although I don't run the servers for a long time, I still want, sometimes when I do some resilvering or some rebuilding of or scrubbing or anything like that, I don't want it to consume a lot of power and unnecessarily waste electricity power consumption. It's just not about power consumption. In case if there is any power failure, I can run this type of a build for more time on an UPS. So all these things I need to take into consideration when I build something like this. And of course it is interesting, although you sacrifice on several things, you need to also make sure what is the end performance you are getting on a build like this, because in this system I'm not running any VMs or something like that, so I need a very bare minimum per core performance. And since it's a very basic FreeNAS, when you do rsync or when you do some file copy, if you enable compression or if you enable dedupe, you need to see how it performs. Again, in my case, I have not enabled compression for all the datasets. Few datasets I have disabled. I know that it is just going to be tarballs, and few datasets I have enabled. So all these factors comes into the place, and this is a nice research when you do an optimization of your NAS server if you are just a user of NAS servers. Whereas if you are a systems guy like me, then I may do even I may architect my own custom built NAS server or some other stuff, and this type of research will help me in terms of scaling up something else. Okay, so that's the overall intent of this entire stuff. So I thought it's an interesting study. I thought of covering in an episode. I don't mind which system is faster and which system is slower. I want to see like with the cache how it performs, with some temperature changes how it performs, with some load how it performs, and I need to see all this things in the real time. So that's when I thought, let me write something like this and let me just assess its memcpy performance. It's what memcpy most of the times you write any stack, you do any software module, most of the times it is just you may do memcpy, memsets and other stuff. So you may do a lot of memory logistics from here to there and stuff like that. So that's why it makes more sense to assess this performance. And even in a CPU performance, even in the case like a true bench, I mainly measure this type of performance. Okay, so I'm not bothered about its CPU ALU's performance, CPU computational power and stuff. It's finally it all boils down to CPU and memory bus interface, how optimized is this interface is. So hope you guys loved watching this video. So with this I would like to conclude the same. If you have anything to discuss, be in touch via mail. Thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.